Okay, I just want to go over a couple of the practice exam solutions here. So number one, we have a true false. Notice a couple things. One, my odd integer, I used the letter k as my 2k plus 1, whereas in my even integer I used an m. I didn't want to use the same letter because the even integer could be 2 times a different integer than the k from the odd over here. So important part there is using the different ones. And notice this is not a exhaustive proof or anything. It's a very quick sketch of why the answer is true, a very quick support. And on the true false, that is plenty to put. Here, false is a pretty easy thing to do because you can show a counter example and that will be plenty of support. This one's a little bit confusing because we're saying for all integers n and d, d does not divide n if and only if there exists an integer k such that n is not equal to kd. So all I need to do is find an example where there's an n and a d where n does not equal kd, but d still divides n, and there would be plenty of examples for that. Third one, this one just takes a little bit of manipulations with the summations, and it turns out it actually almost is true. The only problem is when this k gets replaced by the j minus 1, that does affect this number here, this 11 at the final step. So just a little more intro here on this problem. This sum right here is in terms of k, whereas this one is in terms of j, and the answer is in terms of j. Now I could have converted both of my j's to k's, but it was easier to convert one sum than to convert two. So that's why I chose to convert my k to a j. Now, how would I do that? Well, I want to bring my summation up to start with the same number here. So I want this to start with 1 and go to n. And in order to do that, I need to bump it up by 1. So by replacing my k by j minus 1 and then solving for j, I end up letting j go from 1 to n, and so I can add across. Notice if this original k was 1 to n right here, and this is j equals 1 to n, j equals 1 to n, all I would have needed to do was replace my k's with a j, and then I could combine them. You can combine sums as long as they're going from the same starting point and ending point. So the variable itself is just a dummy variable. Okay, number 4, general arithmetic sequence. This is basically a definition. These are probably the hardest to know how to support, but I'm just showing, basically putting this in words that each term increases by d. So overall, we're going to have n of these d's. Okay, several ways to do this. I noticed that it's going up by 3. The only problem is we're not starting with the original 3, but we are basically going from 1 to 100, then multiplying each one by 3, except for the fact that we don't have these first 3 terms. And then I replace the summation with the formula here, and this is one of the formulas that you should know for the test. And then this final form here, I'm not real concerned with that because you don't have calculators. On number 6 calculation, you're just substituting in, just keep track of what your k is. So here k is 1, k is 2, k is 3, k is 4. And then if you're organized on these are pretty straightforward, just matching up with the earlier v subscripts and plugging in. Okay, number 7 is discrete office hours. That's you. Okay, and so then we go on to the next step, the induction step, where we replace any n in the original statement with a k plus 1. So we've rewritten it here. And then we just modify it using algebra. So I'm replacing the first k terms with this closed form right here, and adding k plus 1 squared by getting a common denominator, rearranging it, and finally it's in the form right here, which we're looking for. Notice that every k plus 1 there, every n is replaced by a k plus 1 there. Okay. Sorry, here's even, I guess I broke it down even further. So here you can see that 2k plus 3 is actually 2 times what originally was an n there, plus 1. Okay, and the final problem is also an induction, looks a bit different. A few different ways to do this. We actually did a similar one in class, I believe, by factoring out the 5, and so you can take a look here at an alternate way to do it. Actually, you can look at how I did this one with the original base step, and then down the inductive step. But if you want to see an alternate proof, there is book solution to number 8 of section 5.3. Okay, well, thanks for taking a look, and please let me know if you have any questions. Just feel free to email me.